Zoko was supposed to give a talk about something related to this, and so this is like a replacement talk, but it's going to be around the same line of work. First. And second, so I will try to focus on the basics. I thought that the extensions is probably too much to try and get into. I just mentioned that these extensions are joint work with many people. Philippe Bolch, Jean, who's there, ciao Jean, Matteo Tamiozzo, Jörn, Alessandro Malusa, Giovanni Felder, and Richard Wentworth. So I will try to have essentially one part about KZ, then the isomonodromy deformations that we want to quantize, and then showing how they match up. And at the end, whatever time is left, to say something about the extensions. That's the plan, okay? So first I will try to say something about how KZ arise in the standard CFT construction. Then I will try to talk about the Schlesinger system. Schlesinger. Then I will try to say how one quantizes the other, so KZ equal Q Schlesinger, so to speak. And then, if there is some time left, these extensions with all of this. Okay, so the main idea is that, so this now goes, what do I do? And I write here, how do I put this up? What is better? I don't know. This goes up. But then this is fairly low. Okay, you'll tell me. Okay. So KZ, before just jumping in the mathematical construction, I will say something a bit hand-wavy about the WZ and W model. Very, very, very hand-wavy. So there is this W, Z and W model in two-dimensional conformal field theory. So this involves taking some space of fields and some action functional, and then the classical trajectories are obtained by looking at critical values. Like looking at the critical points for the action functional, and there is a quantum analog, okay? So roughly fields are something which look like maps taking values from a Riemann surface. Here is something simple. You can think of it as like, borders in between two one-dimensional manifolds, so something like time evolution of those type of objects with values in G, which is some legal. At this stage, I will not say exactly what G needs to be. Later, it will be very simple. I will just have SLN essentially. And so now you have an action, which is a functional S Ves Zumino Novekov Witte, just S, mapping such fields to numbers. So this is supposed to be a combination of the energy of the field defined in whatever, some standard way, plus a West-Zumino term. And so as I said, now one has the classical trajectory, so the classical evolution. It's you look at the critical points here, and this is, by the principle of least action, the trajectory of this particular field theory. So this is like essentially, if I understand correctly, a non-abelian analog of looking at harmonic functions somehow. And then there is a quantum evolution. And here we have the typical story that one writes something which doesn't quite make sense and then tries to define it more properly. So here one talks about correlation functions which in turn depend on a partition function. And I will only write what the partition function is supposed to be. It's supposed to be some Feynman path integral, something like integral over something of some measure depending on the field, and then an exponential term involving this action here. So you like average over all possible trajectories, not just those here, and then you build into the correlators starting from such an object. So okay, this is difficult to formalize, so one can get at it a bit more geometrically or algebraically. And so if I understand correctly, the idea is that one can try to formalize this particular object as some section of a line bundle over the loop group. So that's somehow the idea. So one can make sense and somehow formalize this e to the minus s of phi via, let me just say, line bundles over the loop group G of Z, which are the points of G in the field of formal Laurent series. I don't want to get into any details, but I would just want to say that dense sections of such are naturally acted on by the loop group, and in the infinitesimal version are acted on by the affine, by the loop algebra, and then the sample extension, the affine Lie algebra. And so naturally, in this viewpoint, to try and formalize this, one is led to consider modules for affine Lie algebras, which turn out to be highest weight. And then essentially the correlators built out of this satisfy some constraint for certain elements of modules for this affine Lie algebra. So instead of trying to construct this, we will say there is some finite dimensional space of sections satisfying some constraint, and Z and the correlation functions are supposed to live inside there. So that's why in what follows up, I will just immediately go to affine Lie algebra modules. Okay, so now I will write something. So this leads to G hat, or let me say, yeah, G hat modules, where I consider the standard central extension of the loop algebra, which is literally just a G tensor, the Formula 1 series, which are actually highest weight. And so again, we get to spaces, the spaces where these correlators are supposed to live are some, we will see tensor product of modules for those algebras, but there are constraints. So constraints, these are some linear partial differential equations for those correlators, which mathematically one can express as flat connections on some vector bundle. So one wrote down this system of equations, and then one can rephrase this as saying there is some base, some bundle whose fibers are those modules, and then there is a flat connection in there. And so constraints for correlators, this leads to flat connections, or let me just say flat bundles. So vector bundles in other flat connections, so whose fibers are such models, so whose fibers are spaces of, I will just say, of coinvariance for those G hat modules there. Okay, so this is, as I said, very hand wavy. I'm not giving any detail, but I just want to say that after all, I can now start talking about the representation theory of G hat. We will have tensor product and coinvariance here, and the idea again is that I'm expressing some constraints satisfied by correlator in this particular model. That's very rough. Very rough idea. So I think this is, well, if there is a book of Ko, no? I think the title is like Topology and Conformal Field Theory, which somehow explains this a bit better in some chapter. So there's a reference for this, just for SO2. Okay. So now let's do, okay, so now I will do something which is completely mathematical now. Okay, now I want to look at those modules here and try to construct this flat connection in some particular example. This is going to be Casey. Okay. So now what do I do? Let G be, let's say, a simple Lie algebra. Let's say in finite dimension. Defined over C, but we can just take SLM for some, integer. Let's say I'm only in the abelian case. You take some integer greater or equal than 2, and you look at the simple Lie algebra. Okay, now I want to define some module for the affine Lie algebra associated with this. In a completely standard way, it's this induction that builds first Verma modules and then the integrable highest weight modules. So this is completely standard. Okay, so how do you do this? You fix an invariant pairing on G. So in this case, they are all multiples of the Killing form. One can take the minimal form, one can formalize this in some, one can normalize this in some nice way, but it's not so relevant. And then we construct this central extension here. So this is just already defined as the loop algebra. This guy here instead depends on the choice of the pairing, okay? So now you construct G hat in the standard way. So this means that I impose the following commutation relation just to be all on the same page. If these are two formulas here is F and G, the bracket here is just going to be the bracket in G of these two elements there times the product, and then a term involving the central element. So you take some residues. And then you impose that K was central, okay? So on this vector space, which is the sum of this plus this line, you now have this Lie. Okay. And now I need to take more data. Okay, now to give the details, it's a bit, I mean, on one hand, maybe this is nicer for people who see this the first time, because then there are, many details. Of course, for the experts, this is probably, yeah. I think I will still give some detail. So fix T in G a Cartan subalgebra. So this just means in this example that I just consider traceless diagonal matrices of size n. Traceless diagonal. Okay, and now you want to consider an affine version of this, but you also want to take something more. You want to take a Borel subalgebra containing this. Okay, then moreover, then we take B in G a Borel subalgebra. So this means that in the standard case, I just take upper triangular matrices. Still traceless. Upper triangular. Okay, and now I consider affine versions of those two. You put T hat, just T plus the central element, which lies in the affine Lie algebra. And then you do B hat, which is slightly more complicated. You put B in degree 0 and then something in a positive degree, namely you put everything else. And then also the central element. This is the affine Borel subalgebra associated with B. Okay, and now the modules I want to construct are done as follows. First, you fix a module for this algebra here, which is actually just going to be given by a character, so a one-dimensional module. And then there is a completely, abstract construction inducing modules from this to a module for the affine Lie algebra. And this is what I will do, okay? So now we choose B, let me say U B hat module. I can think of modules equivalently as for the universal enveloping algebra. So a U B hat module, let's say, I don't know, M, and define some induced module in the U B hat, U G hat M, which can be defined in several ways. Here I give it to you as a tensor product. So this means that UB hat is acting on the left here and on the right there because it's just a subring. And then in the tensor product you impose essentially that the standard generators are UB bilinear. So you can not only move around complex numbers but also elements of this subalgebra there. So now, as I said, it's not just any M, it's a very simple M. It's a one-dimensional module given by a character, okay? So more precise, so namely, you choose chi, a character, is it readable here, of B hat. A character just means giving, a Lie algebra morphism towards C. So this is the same as giving a linear map from the abelianization of that to C. So this is equivalent. So let me just say IE, an element, like let's just say a linear map from the abelianization into C, which I can maybe call lambda instead. No, I will not, because it's not just lambda, sorry. So now, what is this very concretely? You can identify it with T hat. If you just compute this commutator, you will see that that is a natural vector space complement of the derived subalgebra inside there. So I can write this. And so now I must give you an element which is just a linear functional here. But this is just the same as giving, by definition, a linear functional on the Cartan, so what people call a weight, plus a dual, an element in the dual of a root of a line generated by K. That's just a number, okay? And this is the small kappa, which is the level in the W model. So plus chi is uniquely determined by the data of two element lambda kappa, and this pair lies, as I just said, in dual of the Cartan and then a number, just a complex number. Okay, so now I can consider if M is just the one-dimensional module such that B hat X by this character, I can do this. Now this makes perfect sense by taking M this, and you get what is called the affine Verma modules with those parameters, which is by definition the induction as above with these choices. So this is the affine Verma module of given weight and level. Okay, and now, so I'm already fairly happy working with Verma modules, but the true story uses the integrable version. So this is not very relevant for the story I want to speak about, so I will try to go quickly through this, but just for completeness, that's not the true object you want to have, so let me put this here as a parenthetical remark. Actually, what one does is that one fixes actually lambda in what Jörn was calling capital lambda M yesterday, this finite set of labels that appeared in Jörn's talk, which is as follows. You suppose K is a non-negative integer, and then you consider dominant integral weight for the Lie algebra at level K. Let me not say what this is. It's just some finite set sitting inside the hat. And for each such choice, you actually don't just have this module here, but you have a simple quotient, which is what you take. So there is some maximal proper submodule. You kill it, and you get some simple quotient, which is now the integrable highest weight module. So this is what you actually want to do. So you get, what people usually denote, I guess, H lambda K, which is the integrable version. Let me just say the integrable module for the affine Lie algebra. Okay? Right. Okay, so now the idea is the following. This is the local construction. So far there is no geometry, I have fixed no Riemann surfaces, no nothing. So now one must imagine that I have insertion of fields in CFT, and at each point, at each, let's say, mark point of Riemann surface, I want to put such an object. And then I have several over the mark points, and then I can start to, deform them and have a bundle where this moves, okay? So now you let sigma be just the Riemann sphere, so I will do only the genus one case here. And I immediately want to think of this, as C union infinity, so you fix one point, let's call it infinity. And so here on the complement, I have the standard affine chart, identifying this with C, okay? I fix the standard coordinate Z. And then I consider mark points, so a tuple, let me call it A underlined, of mark points. Distinct. In this case, they are ordered. And now you build a tensor product of modules at each of those mark points. Okay, so here I fixed an integer. To avoid the complicated discussion, suppose I have at least 3 mark points. Okay? And so now I do the following. I construct H hat, a different H, which is the tensor product of such integrable highest weight modules, where I fixed some level and where I take a tuple of dominant integrable weight of that level. So now this makes sense. I can consider this tensor product. Okay, and now because we are supposed to have conformal symmetry, this is CFT, we are supposed to have conformal symmetries. This is a huge space, but the interest of Belavin, Polyakov, Zamolodchikov in these papers in the 80s was that there are a lot of symmetries involved in dimension 2. So there will be a huge Lie algebra acting here, and these conformal blocks will be obtained by killing this action after all. So what is it exactly? So about the symmetries, you consider let G star, let me just write it, let me think let's just say G sigma A, underline, let this be the Lie algebra of G-valued meromorphic functions on sigma with poles at those mark points. Please.
Could you raise the board a little bit?
I can. Credit to Dr. Nikolai for introducing this notation for positions. Sorry, yes. Yes, so, sorry, let's get serious again immediately. G-valued meromorphic function with poles there. This is the Lie algebra which acts here. And now I will write the action, and it's the most natural thing you can imagine. You have some such rational function, you look at the mark point, and I can take the formal, or let's just say the Laurent expansion there, and this acts on each module by construction, because those are modules for G hat, so in particular for the loop algebra sitting inside there. So you act by simultaneous Laurent expansions of this algebra on that tensor product there.
Sorry, I think I'm
Please.
lost.
Sorry, yes, please.
I lost the bigger picture now.
Yes,
so
tell me.
What is, after you have this integral thing,
Now
what are you doing?
Now I have finitely many such integrable modules. I attach, so I just consider their tensor product, and I want to think of them as being attached to mark points on the sphere. And now I'm going to act on this tensor product and take a quotient of that. And this gives me the space of conformal blocks. Okay, so now as I said, there is this tau I from G star G sigma A into G of Zi, which is just the map taking the Laurent development of a function at that particular point. So this is just the Laurent expansion map. And then there is this lemma, which I'm not going, I'm just whatever. There is this lemma, which is that if I define tau F to be the sum over all mark points, yes, of this Laurent development of F, which I then let act on the ith slot of the tensor product, this here defines a morphism of the algebras from this to the endomorphism of the tensor product, and this is a Lie algebra morphism. So this is a Lie algebra morphism from G star A underlined into the Lie algebra of endomorphisms here equipped with the commutator.
I have a question.
Please.
You take the tensor product of modules. They
Yes.
are modules over the universal enveloping algebra.
They are modules for, for the affine Lie algebra, but equivalently for the universal enveloping algebra of that.
Product is the regular one in the
There are no completions right now. This is, yes, it's purely algebraic, yes. Yes. Okay. So, what is this saying? This is saying that on the one hand, on this Lie algebra here, I do not have the central extension. This is just, the bracket is just obtaining by bracketing the G part. But here, if I do the commutator, I also have the, the central element appearing. And this is still true because the new, this new term vanishes because the sum of the residues of a meromorphic one form on the sphere vanishes. So this geometric fact, because I'm on the compact sphere, not just on the complex plane, but on the, in compactification, I have this statement here. So I'm using compactness here. And so now the definitions are what I said. I take the co-invariance or maybe the invariance of H to get the conformal blocks. So I can say that WZ and W covacua. I think this is terminology, covacua. This is the space V dagger. Let's put a dagger as if it's supposed to be the dual of something else. So this depends on many choices. This depends on sigma, the points, the Lie algebra, the level, the weights, and also secretly on this choice of, what was that I? Apologies. This is a coordinate vanishing at the mark point AI. I didn't say it. So Zi is just Z minus Ti, and in turn Ti is the coordinate of the ith mark point. So because all points are at finite distance, I can take their coordinate. And then this is a local coordinate vanishing there, and so now this makes sense. Sorry. So here I am using explicitly this choice. There is some intrinsic way for doing it, but whatever. And so this in principle depends on this, okay? And so what is this? This is that tensor product where I kill the action of this infinite dimensional Lie algebra. And now these are the covacua. The conformal blocks are typically taken to be the dual of this. So I define the vacua, which are the conformal blocks. So vacua V, depending on the same set of choices, you take the G sigma A linear functions from H to C. So linear functions which are invariant under the dual version of this action here. Wow. I guess let's say, fewer details are going to come in what follows, because otherwise it's too much. Okay, so now this was over a point. Now we vary some parameter, and I want to have a flat bundle of those. Okay, so what will I vary? I can vary many things, right? I can vary sigma, not so much because the complex structure is rigid, but I can vary the mark points, and in principle the rest. Let me only vary the positions of the mark points. Okay, so you now consider B, which is the space of ordered tuples of mark points in C, so Cn minus all of the diagonals. And now I will just state that one can extend this construction from some space over a point to a sheaf over this space here. And then one can prove this is not just any sheaf, but it's actually it's just a flat vector bundle in this case. So in particular, it is locally free, okay? So one extends this to, let me just say, flat vector bundle. V with a dagger or not, whatever, over V. And I will just say very briefly how one does it. First, you take the trivial bundle with this fiber here. And then you want to have a connection there, which is flat and which is equivariant with respect to this action. So one can do this with the Virasoro action of the element L minus 1. So that's the idea here. You use this Virasoro uniformization for the tangent bundle of not exactly B, but if I took this up to the diagonal PSL2C action, I would get M0n, and that's why the Virasoro generators are natural in this story. Okay, they describe the deformations of this. So using L minus 1, an element of the Virasoro algebra, you get a flat connection, which is G sigma A equivariant, a flat GeoEgger connection on actually the trivial bundle with this fiber, which then induces a connection here precisely because I'm taking the G sigma A invariant elements. So this induces a a flat connection. I should say G invariant now. On this bundle here. And this is the KZ connection, okay? You write down the definition of L minus 1, and you understand how this acts only on the conformal blocks where you have a few relation. You rewrite the result for the L minus 1 action, and you get the equation that we saw yesterday in Stock, okay? So you get a connection which, if I just write in terms of, you know, the covariant derivative, this just differentiates up to some constant local sections. So psi is a local section, this is the dual Coxeter number, and this omega ij is the action of capital omega on the ith and jth slot, and omega is what was small t in Anton stock. It's the canonical, you know, quadratic tensor of the quadratic Lie algebra. Where you fix an orthonormal basis of the Lie algebra.
Gabriele?
Please.
Zi here was a local coordinator only.
No, this is not.
Yeah, but the left hand side.
Ah, yes. Thank you. T. Because, this is good. Because now I can consider those. Yeah, thank you. These are now numbers, and because I have this Z which is globally defined on the affine chart, these are global coordinates on B. So it makes sense to say that a connection is given by a global one form, because I can trivialize the cotangent bundle to B using those coordinates. So that's why this makes sense, yes. Thank you. So for, I was saying, orthonormal basis of G. There are many remarks one can make. I will just say that this being flat is equivalent to the classical Yang-Baxter equation for a rational function involving omega. So it's the spectral parameter version of, again, what was in Anton stock, first. And second, since this is flat, you get a monodromy representation of the fundamental group of the base, which is the pure braid group on n strands. And so this naturally acts on this space of conformal blocks. And this is what enters into this famous Kono-Drinfeld theorem relating to the Jimbo-Drinfeld quantum group. Okay, so I will just say that, recall, there is some interesting action of the pure braid group. Okay, Pn actions for Pn, the fundamental group of this, they say at the tuple 1 up to n. Okay, very good. So that's it. Now I want to, so this is a fairly involutive construction, although completely standard. Now, in the second part, so now what I would like to say is that there is an easier, more direct way to find exactly this KZ equation here, starting from isomonodromic deformations of a system with simple pose on the sphere. Okay, so the remark is the following: if you look a bit at this space here, and then taking the reduction, there is another description of this. So for K big enough, one actually has an isomorphism of, let's say, the bundle of vacua, so the conformal blocks, with just the G invariant functions on something which I can call H without a hat now, which is the tensor product of the simple modules for the finite dimensional algebra. So you have a simple G modules. So already here one can make a quantization statement, but I will not say too much about it. So now this looks like a G invariant part of this tensor product here. And so this looks like a quantization of a product of orbits for this group after you take symplectic reduction mod G. And this is actually exactly what brings up, the bridge towards logarithmic connection. So this looks like a Q version of some space which I can write, and the notation is relevant for later on, M Delan star or whatever, a space which looks like O lambda 1 product O lambda n, symplectic reduction at 0 with respect to G, where those are semi-simple orbits passing through this weight here. And there are ways to make this more precise, okay? You mentioned one yesterday. Indeed, one can think of this as a geometric quantization of this product of orbits. And this is done by constructing certain line bundles on the orbit, essentially by the Borel-Weil construction, which I'm not going to use in any way. And there are also statements in deformation quantization, which is more like if you take the Verma modules and you take the endomorphisms of those, they give a deformation quantization of the ring of functions on the orbit. Okay? So there is also something in this direction here. There is work, so well, let me just say deformation quantization. So there is something like, roughly speaking, end of the finite Verma module for the Lie algebra here, the UG Verma module, deforms the ring of functions on those O lambda I, which are Poisson, okay? So and this goes back, so to work, I've read papers about this of Donin and Mudrov, but also there is work of Anton and Anna Chowska. Also there is Damien Kalak, Florian also have something about this. I don't want to get into too many details. I just want to say that there is a deformation quantization statement where, again, these modules, and so a transfer product of them, G-invariant part, is related to a quantization of this space. In two different ways, okay? There is also geometric quantization. Okay, so now if I am able to give some more intrinsic, meaning to this space here, which right now is completely extrinsic, like some product of orbits, then maybe we are happier because there is more geometric intuition. And indeed, this is called like this, because that's the Delan space of logarithmic connection with simple poles on the sphere, and the star just recalls that I am on a trivial vector bundle. So now I will explain very briefly how this works, and finally how I get back Kz by quantizing the isomonodromic deformations. How's it going? Is it okay? Okay. So now 2. Yes. So let V, a different V, never used before, I hope, this symbol. This is now just the trivial rank M vector bundle over sigma, which is still CP1. Okay, now I want to put the logarithmic connection there. Since this is trivial, I can just define it by a global one form. So you consider something completely explicit, A, which is just a sum over all mark points. I keep, the same notation as before, lambda I, z minus ti, dz. And those are elements of G. G I can identify with the dual in some pairing. Let's not bother too much with this or the dual, okay? This is now one form with residues lambda I at those mark points here, and so it defines a logarithmic connection on this trivial vector bundle. Or a Fuchsian system, if you want, in more concrete terms, because this bundle is trivial. Now, what about the modular space? Naively, I can consider this up to gauge without talking about stability conditions. So if I do this naively, what is the gauge group here? I want to have, holomorphic gauge transformations because this is a holomorphic vector bundle. But if I just have global maps which are holomorphic from sigma to GLN M, they're just constant. Okay? So here I just have constant gauge transformation in the holomorphic sense, and this is what I take. So gauge just means that A gets mapped to G of A, which is the same object, but now I apply the adjoint action of each of those. And again, I could put the coadjoint action if I prefer, but that's not so important. You can still think of G as just being, the group SL and C. Okay, so really think that those residues are traced as matrices. I act by unit determinant ones. It's completely, you know, we don't do other reductive groups or simple groups, whatever. Okay, but then what are the choices involved in this space here? I give you the tuple of residues, I fix the positions of the points, and then I just get everything like that. This completely encodes this object here, okay? So you have a tuple of, you know, elements in the Lie algebra, cross completely independently an element in the base B, because now I fix some positions of the points, and then you kill only on the residue part the action of G. So you get, let me put an O here, because I will have a Poisson version and then a symplectic version, apologies. So we get to the Poisson version of the modular space, which is just the space of tuples of residues like this, such that their sum is 0, because I want to have no residue at infinity. I really want to have simple poles only the Mar parts, and then I kill the G action. And this is some singular Poisson scheme, I don't know. Anyway, I'm going to take the symplectic version soon. How do I do it? I now restrict each residue to lie in some prescribed orbit, because you see that here, if I start from some residue, I can only move in its orbit up to the gauge action. So I can restrict and take a symplectic leaf in this space here by fixing these orbits, okay? So if you now let O be a tuple of orbits, in principle, again, coadjoint, but I can move them around, you get exactly that space here. Which now is symplectic, okay? Because each orbit carries the Kirillov Kostanz-Fourier structure, and then there is the symplectic reduction. It's going to be standard. So this is a very baby example of the Ram space. It is somehow the simplest possible thing you can consider if you want to close, okay? I am on the sphere, and I put this star here to remember that there is a global version, let's do it here, where I don't put a star, and now I consider logarithmic connections which can live on potentially non-trivial vector bundles. So these bundles will only be, you know, degree 0, so like topologically trivial, but not holomorphically trivial, and this sits inside there. This is nicer because then it's equivalent to, you know, linear systems of ODEs, and it's enough for this KZ business. So that's why, yes.
Your lambda was discrete there, so maybe you want to choose.
What? Sorry?
Your lambda was discrete there,
This is true. Yes.
So there, to match it, it's a discrete choices of the.
Yes. Yeah. You're right. Apologies. Yes. I said that. This is a nice question. This is called capital lambda I and lies in G. This should match up with the small lambda I using the invariant pairing. Yeah, this is a nice question. So, yeah, you're right, sorry. So here I match up lambda I in P plus K from before. I don't recall if the P was up or down. With lambda I in G. So, or if you prefer, in T then. Okay, I only consider semi-simple residues because this pairing maps the Cartan to the dual Cartan. Okay, it's invariant. So I can do this. Yes?
Can you say why the gauge transformations are constant?
Because you want holomorphic maps from a compact manifold to GLM, so there's nothing else. Yeah. There are no non-constant holomorphic maps. And so, yeah, you're right, sorry, the big lambdas are supposed to match up with the weights in this way here. So still discrete choices if you want to have the nice integrable weight description. If you just want to do the Verma modules, like I can do whatever, right? If I don't care about integrability. Very nice. I mean, I hope you find it very nice. Okay, so now what do I do? Right, so now I want to consider isomonodromic deformations of this, and here I will not give many details, okay? So let me just say that I now take an element here, I think of this as a connection like that. You now look on the sphere, let me draw a picture, the picture that one draws all the time. You're on the sphere, infinity is maybe here, I maybe have a base point B, and I maybe have a mark point AI, which is not B, and then I loop around with some path gamma I. And now what happens is that if I have a local solution, a local horizontal section to this connection here, you do the loop, you go back, and you're going to get something which is not the same as before. There is, monodromy. So there is some automorphism of the fiber which controls this, but because it's a trivial vector bundle, it's just an element of G itself, because it's just a linear automorphism of C to the power n, okay? And so this gives me the standard monodromy data. Of A, which again I identified with a connection, which is something like the class of, so first I have some nu of A, which is a representation of the fundamental group of the puncture curve based at this base point B with values in G. And this sigma O is just sigma minus all the mark points. And then you actually want to take this only up to conjugation because you want this to be the monodromy data of the gauge class of the connection, right? So if I act by simultaneous adjoint action, here I want to act by simultaneous conjugation. And you get a space which is now much closer to the Carter varieties that we saw again in Anton's talk. Only that he was doing the version with and without boundaries, and here it's more about adding, the puncture case, but of course there are relations. So it's G conjugacy class lies in what sometimes people call MB, the Betti space, but that's just the Carter variety. Okay? I will say, this is not super relevant, but just as this looks like, this is a symplectic reduction, okay, because this is exactly the zero condition for the moment map written here. The sum of the residues vanishing is exactly the same as saying that for the standard moment map on the product of the orbits, you take only those that map to zero under a moment map and then you reduce. So this is a Hamiltonian reduction. This can be interpreted as a quasi-Hamiltonian reduction. There is a completely analogous story here. So this is tuples G in G to the n, whose product is equal to 1. I have an order, so this makes sense. I have order points. And then mod G, okay? So if you want, one can also put a double bar there, I guess, but okay. So this is like Q Hamiltonian reduction, quasi. Again, and so this is again, originally, if I understand correctly, work of, Anton, Alex, and Milankin, right? So this is nice because now I have this additive quotient which maps to a multiplicative quotient, and what I'm saying is that Kz is a quantization of the additive version. So I use this to speak about monodromy data, but I'm not so much about the quantization of this, okay? It's really about the quantization of the RAM. That's, I think, an important point. This involves something different which I'm not using today. Okay, so now I have the monodromy data. Now I want to have isomonodromic deformations. This means that monodromy should remain constant, isomonodromic. So what do? You now move again B. So you move inside B. So you now move the tuple of the positions of the poles in B. And now what you do is that if I move them ever so slightly, these points here, you see that I can put a small disk essentially around here such that I can fix the generators of the fundamental group if those move only a little bit in some polydisk, okay, inside of B. And so if I fix this generator, I can make sense of monodromy constant locally under small deformations here. And this is what you impose, okay? So impose essentially nu this monodromy map there to be locally constant. And now this brings another flat connection, but now in the semi-classical world. So it's a non-linear flat connection on a bundle of varieties, precisely the bundle of those varieties here, in the Poisson or in the symplectic version, or, and it's like essentially an equivalent statement, on a bundle of those character varieties. So this is completely analogous. So you get flat, let me specify Hairesman connection on, let me just say, on the trivial fiber bundle, Poisson or symplectic, however you want, fibering over B. But we can be more concrete about this. We can say that it is actually coded by a Hamiltonian system, and this is the Schlesinger system that I put at the beginning of the talk. So this is equivalent to certain nonlinear now partial differential equations, which are coded by a certain Hamiltonian system here. I will write down the Hamiltonians, and then we will see that if I quantize them, I get Kz again. So that's how one gets Kz from these isomonodromic deformations. So now, equivalent to nonlinear PDEs, more precisely, the flow of non-autonomous integrable Hamiltonian system. Let me just write Hamiltonian system, whose Hamiltonians look like Hi going from Gn cross B into C. Then they will, they will descend to the reduction, but I can define them already at this stage. And these are just Hi on lambda and T equal sum J different from I, and then I put the invariant pairing and I divide by Ti minus Tj. So this is a non-trivial statement. I'm saying that if you impose that these deformations are locally preserving the monodromy representation, then it's equivalent to just say you deform. So what do I mean by the linear equation? I mean that you write differential equation for the residues as a function of the positions of the poles. You say, if I vary the positions ever so slightly, how should the residue vary so that this is constant? And you find that this is controlled by the flow of these equations, of these Hamiltonians. So that's the statement. And this goes back to Schlesinger. Okay, so this goes back to something which is like around the beginning of the 20th century. Okay, so the deformations of Fuchsian systems on the sphere. And now what we see is that I have these nice quadratic Hamiltonians there, and there is now a completely straightforward quantization procedure such that applied to this, I get back the Hamiltonians of the Kz connection that I had before. So that's the end of like this story. And now it's completely direct. So I will write this. So note that this is a function depending on the residues and the positions of the points, but you can freeze the positions here and just getting a map from G to the N to B. So if I freeze, I get Hi restricted to G to the N cross one particular positions of the points. And this is now a quadratic function on a tuple of, an n tuple of elements in the residue. So this naturally lies in Sim G to the tensor N. And again, let me identify G with the dual, please, okay? So it naturally lies there. And so now we can just invoke the standard filtered quantization of the symmetric algebra to get the universal enveloping algebra, which is a very particular case of deformation quantization. I can just do this, okay? I can now just say that formally I should say that like the Riesz algebra of UG provides a deformation quantization of this algebra here of Sim G, and then you just put tensor products everywhere, okay? Not only this, but there is also a map, completely canonical, which maps from the symmetric algebra to the universal enveloping algebra, which normally is not so helpful to construct quantization because it doesn't preserve any relevant structure, but here it does. So on the nose we just get Kz and it's going to be flat, and that's it, okay? So there is a canonical map, a canonical G-module isomorphism from the symmetric algebra to the universal enveloping algebra, which just involves taking, the action of the symmetric group and mapping symmetric tensors to element of the universal enveloping algebra. And one checks, and so this is now fairly straightforward, so I was hoping to do this in some detail, but clearly I will not. One checks that if I call this like, I don't know, how do I call it? C, because it's the canonical mapping. One checks that if I now do C tensor N after HI, and I call this HI hat, this is now a map from G into UG tensor N. So because of this statement, I can think of HI as a map that for each point gives me an element here. So the classical Hamiltonian is a function from B into sim G to some power. And then I just apply this tensor-wise, and now I get something which maps from here into UG to the tensor N, and one shows the following formula, is just HI hat equal, you now lose the parameter, but it's the same story, omega ij over Ti minus dj. So you just get back exactly what appeared in this linear PDEs given by Kz, and so now this means that Kz is equivalent to the following, Heisenberg type evolution equations, I guess, so that you write dTj over psi hat, which is a section of the bundle, I was calling it psi, I guess, a section of the bundle of conformal block, up to some factor, which I can ignore, the commutator with this. Sorry, Schrödinger types equation, so it's multiplied by this. Apologies. Yes. So this was observed not in these terms, first by Reshetikin and Arnold, okay, this observation. So this goes back to Nikolai Reshetikin and John Arnold. I think 19, whatever, something like that. Now I could be a gentleman and stop here, and I did, is equal. But I really want to say something about that. I will just move my hands around and say something about the extensions without writing, I guess, if I may. So this is known since, I don't know, whatever, now 30 years more. We are doing new things, okay? It's not just this. So what are we trying to generalize with Philip, Jean, Giovanni, Richard, Matteo, Alessandro, etc.? So we would like to generalize essentially two ingredients. We would like to generalize this, as I said, or maybe even this. And then we would like to generalize B, which I hope I still, okay, yeah, sure. We would like to generalize this. And then to quantize this in more general ways. So in brief, instead of just taking logarithmic connections on the sphere, there is now a completely general topological theory for isomonodromy deformations, which I take from the papers of Philip, Bolch, from 2001 up to 2015, essentially, where much more general isomonodromy deformations can still be interpreted as flat symplectic Hellesman connections, where this is now more general, or rather this is what people call sometimes the wild-Carter variety. And B is more general because now I have more parameters to deform. I don't just deform the underlying pointed Riemann surface, but I deform what we call a wild Riemann surface, so where there are more data involved here. And so the end goal somehow of this story would be to consider arbitrary deformations of those wild Riemann surfaces, which should involve a generalization of the stack MGN with these new parameters there, fibering over that. This here should be replaced or that by the most general version of wild-Carter varieties or the Ram spaces. And then you want to quantize, and this, what I'm concretely doing with Giovanni and Richard, we have this preprint in preparation, where we construct new modules, generalizing the Verma modules, and then hopefully later the integrable modules, which we call singularity modules because they're attached to any possible singularity. And now they quantize not, in principle, those orbits for just the residues, but orbits where you can have a form A, that I erase now, which also have irregular coefficients. So these are now orbits for gauge, these are gauge orbits for principal parts of meromorphic connections beyond the residues. So these modules would quantize that, and hopefully those nonlinear flat connections after quantization become linear. And so this hopefully is related to some irregular version of WZ and W, okay? So it's like a WZ and W version of what I guess Gaiotto, Teschner, Aldei, Tachikalo, Gaiotto, Teschner, and all these people did for revealed theory, hopefully, but this is very, far away. That's it. Thank you very much.
Okay, questions or comments?
So in the WW side, do you expect it to be non-high-sway type modules?
There is this work of Fagin, Frankel, and Toledano Laredo where they have non-highest weight modules. So I spoke with I really would like to have something which turns into a quantization of the RAM spaces, and what we found actually are highest weight modules. So it's somehow a different construction. Very briefly, they look something like, they are still, in the Verma version, they are still induced. Forget about the symbols are not relevant. So A is like a principal part, and this psi is something else, whatever. And so I'm still inducing from some subalgebra involving chase of parabolic subalgebras inside G. That's the new stuff. So not just Borel, but parabolic, and not just one, but several, because I have several. And so now I still have a natural Cartan subalgebra in there, and I still get T-weight modules. And I have a cyclic vector, which is, highest weight because I choose a parabolic. So I also have a choice of positive roots, and I get a highest one. So yes, actually, we do get something which is still highest weight in this construction. And this was not your question, but I would like to add that the cyclic vector in here, if you act by Virasoro, you still can. You do recover those Gaiotto-Teschner irregular states, these Whittaker vectors that appear in Uville under the Virasoro action. So that's why, I don't know, it's at least a bit promising, I don't know.
Questions?
Can I ask a question? So
Please.
maybe it's a related question, but at some point you impose that the rebel is a positive integer or something? I mean,
Yes.
Yes. So is that how this is important in your
No, exactly. Right, so... No, this is, so I went quickly. So the representation theory of finely algebra is like you have the Verma, and then you take an integrable quotient which behaves better, essentially because it contains the simple module rather than the Verma module. So if you're interested in getting the simple representation and like the Verlin, the formula and stuff like this, you need to have this restriction. And so this concretely meant it's what Jörn wrote yesterday. You want a weight which is integral, so it maps any co-root to integers in the lattice. And then if you take the highest root in the simple case, you want this to be smaller or equal than k. So you bound it this way here. And then you do find these quotients here. But as I said, there is a deformation quantization statement for semi-simple orbit which are not integral. So I can do more, I guess, yeah.
So in the WW side, then you have to analytically continue the level to complex values.
Can you repeat? Sorry, what?
He was asking the integral levels in the WW side.
Yeah, but exactly.
For that, you have to analytically continue the level k.
Right, so if I do a continuous level k, then I don't even try to impose this, and I just have the Verma modules. So, which still maybe is a deformation quantization of those orbits, but then it's less close to conformal blocks, right? So, yeah. Yes. I don't know. Yes, please.
So in your Schrödinger equation,
Yes.
the Planck's constant is k plus something?
Yes, right. So here, if I just do this symmetrization map on the nose, I don't get any kappa, any dual Coxeter number. But yeah, you're right. So if I put something like a different kappa here, like kappa prime, I don't know, this is what then you can take the, asymptotic to get back to the semi-classical stuff. And it was, kappa It's related to kappa plus the dual Coxeter number, absolutely, yes.
But then sending it to zero contradicts your integer.
I don't know, but yeah, right, absolutely, yeah. So that's why I'm saying either you do this conformal block stuff and then you argue that this is deformation quantization in a different way, or instead you have this, much more direct approach, and then I agree you have to allow for non-integer levels to have any orbit, but then you cannot just send this stuff to zero freely. Yeah, sure. I agree, yeah.
About the Schrödinger equation,
Please.
This psi has a asymptotic behavior at infinite k. So looks like exponential k plus h hat and something like a function s, let's say.
Fair enough.
And this Schrödinger equation reduces what's called the Hamilton-Jacobi equation for the isomonodromy flow. Can you formulate that using your quantization scheme?
I think Reshetikhin did exactly what you are saying, right? Reshetikhin started from the quantum case and he just said, wait, I take this limit, and so the semi-classical limit of Kz is now Schlesinger or generalization. Here I do the other way around. Instead of saying I have a quantum object which reduces to this, I took some classical object and I constructed for you some quantum one, which tautologically gives me now this back. Because I use this symmetrization map, and it's now completely tautological that if you do the Riesz algebra of that and you put h bar to 0, you do get back the starting Hamiltonians. So I inverted the original viewpoint, I guess.
Okay. If there are no other questions, let's thank Gabriele again.